good morning and welcome to our science lesson. We are still on waves and we have been looking at characteristics of waves and how we can manage to describe our waves fully. Now, we classified different waves and we found out that there are some characteristics that govern the behavior of a wave. Now, we are still on those, and the last aspect was number 5, which we looked at the wavelength of a wave. And we said that this one basically is the distance between 2 points on a wave train that are in phase. We looked at what we mean by waves in phase. We said that is where particles are moving in the same direction and at the same level of displacement. Now, the regions that would exhibit points where on a wave where particles would be in phase are what we are interested in here. And we took an example of a transverse wave. We took an example of a transverse wave where we could have a plot. Of displacement against time in seconds. This one is displacement. Again, it is in meters. Now, we can manage to get or to locate 2 points which are in phase. For example, if you look at points A and B, this one is A and B. If you consider points A and B, you find that both of them are on the maximum height. They are on the maximum height of a crest. Both of them are crests and are the maximum heights. That is why we say the distance between them. The distance between them is what we call the wavelength. Again, you could consider other points. You could consider other points, say C and D. C and D are at the bottom of the troughs, and these are successive troughs. So the points on successive regions that are in phase are what we call the distance between points that are in phase is what we call the wavelength. We could also consider a longitudinal wave, which is characterized by a series of compressions and rare functions. Compressions and rare functions, and we could consider a point A. We could consider a point A and another one B. both of which are at regions of compression. You could also consider C and D, which are at regions of rare functions. Now these 2 points are successive and at the same level of displacement on the wave train, and that is why we talk about them as being in phase, and that now the distance between them, this distance here, is a lambda, or what we call the wavelength, or you could even take it to be the other one. Either of them, it shows the wavelength. Now, the last characteristic that we have is what we call the speed of a wave. Speed of a wave. The speed of a wave, this one is the distance, covered by a wave. Distance covered by a wave in 1 second. It's actually the distance covered by a wave in 1 second, and it is given in meters per second. The distance covered by a wave in 1 second, and we give it in meters per second, just like speed in any other function in physics. We give it in meters per second, and this case is no different. Now we can look at the relationship that exists between speed, wavelength, and frequency. Speed, wavelength, and frequency of waves. Is there a relationship that exists among the three? And normally, speed, which in this case we are going to symbolize using a V, speed is given by distance over time. Now, in case of waves, we do not talk about distance, but the wavelength. The wavelength. And the speed, we have given it letter V. Time, we can also give it T. Now, therefore, this implies that our V is going to be equal to lambda over T. But we know that time is given by 1 over frequency. Therefore, we can substitute for time in our equation star so that now equation star becomes, so substituting for T in star, that speed is equal to distance divided by time T. and we call this one star. We say but T is given by 1 over frequency. Therefore, substituting for T in star is going to give us V being equal to lambda over 1 over frequency, which is the same as lambda multiplied by F over 1. Therefore, V is given by frequency times wavelength. So basically, this is the relationship that exists between the three. That speed is given by lambda F. Now, let us take an example or two of questions involving this relationship. Before we can analyze it graphically. And example 1, waves on a string are produced. Waves on a string are produced at the rate of 20. At the rate of 20 wavelengths every 5 seconds. Number 1, find the frequency of the wave motion. Now the question that we have here suggests that waves on a string are produced at the rate of 20 wavelengths every 5 seconds. So now we are required to get the frequency of that particular wave train. But frequency is equal to lambda over time. Frequency is given by lambda over time, which is equal to 20 in our case, divided by 5 seconds, which is going to give us a frequency of 4 hertz. Frequency of 4 hertz. Now part B, if the wavelength, this is B, if the wavelength is 0.01 meters, we should find the speed. Find the speed of the wave. If the wavelength is 0.01, now from part A, we found our frequency to be equal to 4 hertz. Now the question further gives us more information that the wavelength is 0.01. So we are required now to get the speed. Now, but from our relationship, Speed is given by frequency multiplied by the wavelength, each of which we have. Therefore, we can just substitute so that now speed is 4 hertz multiplied by 0.01 meters, which is going to give us 0.04 meters per second. 0.04 meters per second. The last part requires us to get the period. Period of the wave. Period of the wave. And we know that period, capital T, is given by 1 over frequency, and our frequency was 4 hertz. Therefore, our period will be a quarter, which is equivalent to 0.25 seconds. 0.25 seconds is the time required to complete one oscillation. Time required to complete one oscillation. Now we can look at yet another question. Another question, example 2. A water wave travels 12 meters. A water wave travels 12 meters in 4 seconds. In 4 seconds. Niposi? A water wave travels 12 meters in 4 seconds. If the frequency of our wave is 2 hertz, then we are required to calculate, number 1, the speed of the wave. Speed of the wave. But speed is given by distance over time. Speed is distance over time. Therefore, we can substitute so that now our distance is given as 12 meters. Time is 4 seconds. Therefore, we have a speed of 3 meters per second. That is the first bit of the question. That we have a wave train traveling at 12 meters every 4 seconds with a frequency of 2 hertz. So we want to find out what is the speed of this wave train, and we can just take the direct formula where speed is given by distance over time. substitute for the same and get our speed as 3 meters per second. Now the second bit of the question, part B, requires us to get the wavelength. The wavelength of the wave. Requires us to get the wavelength of the wave. And again, we go back to our relationship that we have just looked at, where V is given by wavelength multiplied by frequency, and we have found our speed to be 3 meters per second. This is going to be given by wavelength multiplied by our frequency, which is 2 hertz. Let us collect the like terms so that wavelength becomes the subject of the formula, which is going to be given by 3 meters per second, and we divide by 2 hertz, so that now our lambda becomes 1.5 meters. Lambda becomes 1.5 meters. 1.5 meters. Let us look at something to do with graphical analysis of our relationship. Graphical analysis of that. And there are some points that we want to note first. Number one is that the rate of vibration, of a medium, determines the frequency of a wave train. That is the point number one that we can manage to get from our relationship, that the rate of vibration of our medium is going to inform the frequency of the wave train. Number two is that increasing frequency decreases wavelength of a wave train. It actually decreases the wavelength of a wave train. Now look at the relationship that we have. V is given by lambda f, and now we have increased f but held our V constant. Now if the relationship is to hold, then lambda multiplied by frequency at any given time gives the speed of a wave train. Therefore, if you increase frequency of a wave train, it translates to a decrease in the wavelength of the same, and the vice versa is still correct. Now, if we were to draw a graph if we were to draw a graph, of frequency against wavelength, is frequency in hertz, and this one is wavelength in meters. Now, if you were to consider that kind of a graph, it is actually going to be a curve that does not have intercepts. It is a curve that does not have intercepts, implying that decrease in one of the parameters, either lambda or frequency, results to increase in the other. Decrease in one of the parameters will increase the other, and therefore we shall have a graph which is actually a curve that does not have intercepts. Now that's about all to do with characteristics of waves. Now we can say something about properties of waves. Properties of waves. Properties of waves. And properties of waves are equally important to us. Why should we study them? Now, going through the properties of waves will help us to explain different phenomena. They will help us to explain different phenomena. For example, different phenomena. For example, through the study of these properties, we can explain occurrence of the rainbow, we can manage to explain how a rainbow occurs. We can also explain mirages. We can explain variation of sound variation in musical instruments. We can explain that. Why should sound vary in musical instruments? We could also try and explain color observation. Color observation in oil films, among other phenomena. We can explain those among others. Now, to the properties themselves, we start with the simplest. And the simplest property is the wave front. Wave fronts. And a wave front is actually a line drawn joining points that are in phase. Is actually a line joint, a line that is drawn joining points that are in phase. For example, if you had a wave train of transverse type, and then we say that points that are in phase are those ones that are traveling in the same direction and are the same level of displacement. Therefore, all the particles along this line, now that we have our wave train moving in a direction that is perpendicular to the vibration of particles. Therefore, if we were to draw some lines joining any particles vibrating in phase, we would come up with something like that. That we have particles on the medium which were traveling in the same direction at the same level of displacement, we would have something like that. That's a wave front. And number 2, property number 2 is rectilinear. Propagation of waves. Rectilinear propagation of waves. And this one is the straight line travel. The straight line travel property, and it is actually the suggestion that waves will always follow a straight line. Whichever type of waves you are looking at, the direction of motion will always be a straight line. For example, if you had a wave train exhibiting this kind of wave fronts, if these were to be your wave fronts, now if you look at our wave fronts, they are actually advancing towards the right hand side. They are advancing towards the right hand side, indicating that much as we have vibration of particles being shown by our wave fronts, the direction of motion of our wave, the direction of wave travel is actually from left to right, suggesting that our wave is following a straight path. Now, how about if we considered a case of a wave train with circular wave fronts? Say from a point source of waves, we said that a wave is actually transmission of disturbance. So if you disturbed a point source, your wave fronts are going to look like this. You are going to have some circular wave fronts, but they equally advance from the point source towards the far right hand side. So we are justified to take the direction of motion to be a straight line. That is from left to right, and these ones here will now be your wave fronts. An example of this is what we call the water waves. Water waves originate from a point source. They are circular, but they move in a straight line. They advance from the point of disturbance as the center, and they advance towards other directions in a straight line. Now, the third characteristic that we are going to look at, the third characteristic is reflection. Refraction of waves. And like we have looked at light in the past, we said that light can actually be reflected. Now, light is an example of a wave. Light is an example of a wave, whereby we said that light will travel from one point to another and can change direction depending on what it comes across. Basically, we are going to look at how a wave behaves when it comes across an obstacle. So reflection is the bouncing back. It's actually the bouncing back of a wave when it comes across an obstacle. When it comes across an obstacle. In this case, our obstacle, we are going to call it a reflector or a reflecting surface. And depending on the nature of the reflector, we are going to have different wave front shapes depending on the type of reflector. So we can note that depending on type of reflector, the shape of the wave fronts could change or even be maintained. Now we will look at several types of reflectors and see what effect they have on reflection, our wavefronts when they are reflected. we look at different types of reflecting surfaces and see what effect they are going to have on the shape of our wave fronts. Number one, we consider wave fronts incident on a reflector placed at an angle. Placed at an angle to the direction of wave motion. For example, let us assume we have plane waves, and then we have a reflecting surface at an angle to the direction of motion of the wave. We are having plane waves where wavefronts are actually parallel to each other, and then it is incident at an angle to a reflecting surface. Take this one to be our reflecting surface. That's our reflecting surface. Our plane waves are taking the direction from left to right, and then we come across a reflecting surface at an angle. Then we can draw a normal here so that the angle of incidence is given there. An angle of incidence is given there. So what happens? What happens is that our wave is going to be reflected in such a way that I is equal to R. Remember, we are not considering the wavefronts but the direction of wave motion. So in this case, you will expect the direction of wave motion to be in such a way that I is equal to R. So your plane waves will now take this other direction, so that this one is direction of incident wave. This is the direction of the incident wave, and this one here is the direction of the reflected. The direction of the reflected wave. Now clearly you can see that the law of reflection is obeyed, because for us to claim that the law has been obeyed, I should be equal to R, which is the case with our wave here. Let us look at yet another type of reflecting surface. At right angles with the direction of motion of wave train. That one is our reflector. Then we have some plane waves, plane wavefronts, taking a direction perpendicular to the reflecting surface. Now these ones, we expect them to be reflected in such a way that they remain plane, and then we also have a right angle of reflection. So they are going to be sent back in such a way that the angle between the reflecting surface and the direction of motion of the wave are actually right angles. So this one will be incident wave. This is the incident wave. This is the reflected wave. Now remember that the dots, this one is the reflected wave, and the plain ones are the wavefronts of the incident wave. Now let us look at yet another type of reflecting surface. Consider situation C. We consider plane wave incident on a concave reflector. That we have plane waves and we have a concave reflector. Remember, in the case of light, we agreed that this reflector has an effect of converging a beam of light, and in this case we are saying that light is an example of a wave. Now let us consider these plane wavefronts. The plane wavefronts come across a concave reflecting surface. Now, what we expect from this reflector is that it's going to converge our wavefronts before they spread again. Therefore, we have our principal focus somewhere there, and then we expect our waves to be reflected in such a way that they are converged at the principal focus. Before again they spread, so that now they converge and later they diverge. In the initial wave was traveling in that direction, and then our second wave after reflection is going to be in the opposite direction, only that they will converge at a point F, which we call the focal point, before they can then spread out to other regions. How about a convex reflector? How about a convex reflector? How about a convex reflector? Now, a convex reflector actually diverges a wave. But one thing we have to note is that F of a convex reflector is actually virtual. So much as it is diverging our wave, it will look like the wave is diverging from some point, but the wave does not actually pass through that point because it is virtual. Therefore, if we consider a convex reflector, we bring some plane wavefronts, plane wave fronts, so that they are incident on it. This is the direction of incident wave. Now, we expect our wave to diverge, to appear to diverge from a point in front of the reflector, so that now we are going to have our wavefronts changing from plane to circular. They actually change from plane to circular in the opposite direction, and they appear to diverge from some point at the back of the reflector, showing that our reflecting surface is actually convex. Lastly, we can consider circular waves. Incident on a concave reflecting surface. Consider circular waves incident on a concave reflecting surface, so that now we have some wave fronts we have some circular wavefronts from some point here. They are incident on our reflecting surface. Taking this direction, this is the direction of incident wave. That one is actually the direction of the incident wave, and we expect that they are going to be reflected so that they will assume a plane shape. They will assume a plane shape, and they will take the opposite direction. So that now we have the opposite direction being the direction of reflected waves, only that this time they have changed from circular to plane. So clearly we can be able to demonstrate that the shape of the reflecting surface is of utmost importance when it comes to the characteristics of the waves formed after reflection. However, it is good to note that after reflection, speed of a wave does not change. And number two is that the wavelength is also maintained. The wavelength is also maintained. So from the relationship that we've just looked at, we said that V, which is our speed, is given by wavelength times frequency, and we are saying that the speed remains constant. We are also saying that the wavelength remains constant. Therefore, it follows that the frequency is also maintained. So we can note that from this relationship, frequency is also maintained. So what is happening to our wave is that the direction of travel is changing, and probably the shape of the wavefronts will also change, but other characteristics of the wave are going to remain. Now, that marks the end of our lesson. When next we meet, we are going to discuss refraction of waves, and find out what it's all about. Thank you.